Hello everyone. So in this video I'm going to talk about another very powerful theorem called Thevenin's theorem, from the name of the scientist and engineer Thevenin. And it's a very powerful theorem in doing the network circuit analysis. And this theorem is based on the linearity and the superposition principle, which allows to replace a very complex network of resistors and sources with an equivalent circuit containing just a single voltage source and a single resistor in series, as shown in the diagram. So Thevenin's theorem simply says this: any two-terminal linear DC network can be replaced by an equivalent circuit consisting of a voltage source and a series resistor, as shown in the figure. So for example, here in this example, so you can have any complex circuit like this. So you can just imagine this is a black box, right? Any black box consisting of a complex network of resistors and many power sources, both current and voltage sources, right? Thevenin's theorem simply says, now this complex circuit can be just replaced by just a single voltage source, equivalent voltage source called Thevenin's voltage, and a series resistance in series with that Thevenin's voltage called Thevenin's resistance. And there are certain rules to find the equivalent circuit, and this is a very useful circuit, because once you find the equivalent circuit, right, then you can easily find the load current, right? So if you connect a load resistance or any load, then you can easily find the load resistance. It's just now this becomes a series, right? And because without this equivalent circuit, without Thevenin's theorem, it would be very difficult to find the voltage, right, at this node. Every time you change the load, every time you change the different load resistance with different resistance, you will have to recalculate all the nodal voltages. But once you find the Thevenin's equivalent circuit, then it's fixed. The source is fixed. The source and its resistance is fixed. So let's do some example problems based on this, right? So what's the rule? The rules are this. The rules are, so to find the Thevenin's voltage, to find the Thevenin's equivalent voltage, you have to find VTH is Thevenin's voltage, right? It is basically with the load resistor removed, find the voltage across the two terminal and end of the terminal. That's the rule. That's the first rule. So to find the Thevenin's equivalent voltage, you just need to remove the load resistor and find the voltage across the two terminal, right? And how do you find the Thevenin's equivalent resistance? So to find the Thevenin's equivalent resistance, then do the same. With the load resistor or load removed, right, I'm gonna use the word kill all the sources. That means you have to make all the sources zero. So if it is a voltage source, right, if it is a voltage source, then you have to short it. Must be short. Just put a short circuit. Just put a conductor across the voltage source so that the voltage or potential difference across. The only way you can make the voltage zero is just by putting a jumper wire, or just by shorting, or just by a conducting wire across the two terminals, right, so that the voltage becomes zero. So if it is a current source, right, if it is, however, a current source, could be a current source, right? Current sources must be open, right? Just open the current. If it is current source, and the only way you can make the current zero is just open it, right? Just disconnect the current source. And using this idea, using this Thevenin's idea, Thevenin's theorem, we can solve some network problems. So let's get started with some very simple circuit. So on this diagram it says, for the given networks, find the Thevenin's equivalent circuit. So it's asking to convert this circuit. This is the load resistor, by the way. This is just the load resistor. Right? It's just asking, find the Thevenin's equivalent circuit. That means find the equivalent Thevenin's voltage with a series resistor, right? And then you can put the load resistor after that, finding this. This is the Thevenin's resistance, this is the Thevenin's voltage. And then after that, find the load resistor, right? So it's asking you to find the equivalent Thevenin's circuit. So what's the rule? So to find the Thevenin's voltage, first let's find the voltage. So what you have to do based on the rule, so first you have to remove, if there is a load resistance, remove the load. You have to remove the load resistor. So you have then this, right? And you have 3 ohm and 6 ohm. And the load is removed. And whatever voltage you see from this side, right, is the Thevenin's voltage based on the Thevenin's rule. So your voltage is 9 volts, right? And 3 ohms, 6 ohms. So this is your R1, this is your R2, right? So R2, and let's say this is your B in, right? So this is just the voltage divider. The voltage across R2 in this configuration, the voltage across R2 is your Thevenin's voltage, and that's just the voltage divider. So that's going to be just R2 over R1 plus R2 times the source voltage, right? And that's going to be 6 divided by 9 times 9, so it's 6 volt. So your Thevenin equivalent voltage is 6 volt. Now next part is finding the Thevenin's equivalent resistance. And what is the rule? Again, you have to, if there is a load resistor, first your job is to remove the load resistor, right? And then you have to kill all the sources. Then kill or zeros all the power sources. So here in this example, you only have a voltage source, so you just need to put a conductor across it, or you just need to short it. So just make it a short circuit. So voltage source should be short circuit so that the voltage becomes 0, right? And the resistance you are looking from this side is your Thevenin's resistance. Now this is simply nothing. This is just this becomes a parallel combination of 3 ohm and 6 ohm, and that's your Thevenin's resistance. Thevenin's resistance in this example just becomes the parallel combination of 6 and this, right? And that's going to be so we know, just find the parallel combination of this is going to be 2 ohms, right? So our conclusion is now, right, so we found the Thevenin's voltage and we found the Thevenin's equivalent resistance, right? Now go back to this. Now you can convert this whole circuit, let's say a black box circuit. It could be very complex. In this example is relatively simple, but it could be very complex network wrap circuit, right? Is now just this 6 volts and 2 ohms. Now once you have this, right, once you have found the equivalent Thevenin's equivalent circuit, then you can easily find the load current, right, current through the load. And this is the main advantage of using Thevenin's theorem. It's a very powerful technique.